So whenever you're ready, please take away.
Thank you. Thank you for the introduction. So good afternoon and nice to meet you. So I'm Ryo Yokokura from Keio University, Japan. And first of all, I'd like to thank organizers for giving me an opportunity to talk in this great workshop. So it is my first time in Korea. So yes. So today, I'd like to talk about the relation between the topological solitons and non-invertible symmetries in axion electrodynamics. So this talk is based on this paper written with Yoshimasa Hidaka-san. He will come here in the next week, and Muneto-san. So the message of this talk is that the non-invertible symmetries can classify possible configuration of topological solitons. So this is my message. So this is the overview. So we derive selection rules for the configuration of the solitons using non-invertible symmetries in four-dimensional axion electrodynamics. Technically, we identify the magnetic strings and the axionic domain world as non-invertible symmetry generators in the low energy limit. We then show that the correlation functions of the solitons linked with axionic string or the magnetic monopole can vanish. Now, this is the contents of this talk. The first is the introduction. And next, I'd like to review the invertible symmetries in the phase with massive photon without axion. So in this talk, I'd like to call the phase with massive photon, that is the Higgs phase, massive photon phase. Next, I'd like to review the invertible symmetries in massive photon phase with axion. After these review parts, so I'd like to discuss the non-invertible one-form symmetry in the massive photon phase. By using the non-invertible one-form symmetry, I'd like to derive the selection rule for the linked configuration of the axionic and magnetic strings. Finally, I'd like to comment on the selection rules for the linked configuration of the axionic strings, axionic domain world and the magnetic monopole. So let me begin with the introduction. So in this talk, I mainly consider the axion electrodynamics. So this is a system with an axion and a photon and the topological coupling between them. So there are several expressions of the topological coupling. So E dot B or FF tilde and FHF. So here, axion is, at least in my talk, is a pseudoscalar Goldstone boson of U1 symmetry, which can have a chiral anomaly. So represented by this triangle diagram. So there are several features in the axion electrodynamics. So one is that this system is ubiquitous in modern physics, such as QCD axion in particle physics and inflaton, dark matter in cosmology, and Piezo meson in hadron physics, and the modular field in from string theory, and quasi-particle excitation in topological material in the context of the condensed matter physics. Another feature is that the axion and photon are coupled by the topological coupling. In particular, the coupling constant, so the coefficient n is quantized via the chiral anomaly. Furthermore, so there are several phases depending on the masses of the axion and photon. For example, phases with massive axion can arise in the context of the QCD axion, and the phase with massive photon, that is a Higgs phase, can arise in the context of the topological superconductor or the cosmic string and so on. And there can be spatially and or temporally extended objects, depending on the phases. For example, so there can be two kinds of extended objects in the massive photon phase. So let us see the extended object. So one of the objects is so-called axionic domain world. So this is a 2 plus 1 dimensional extended object. So like this. So the axionic domain wall is a soliton, which is a classical solution to the equation motion of the axion, which connect two different minima of the axionic potential. For example, so in this region, so the value of the axion is this one, and in this region, the value of the axion is this one. So, and the axionic domain wall connects to different vacua in the real space-time. So there is a to connect these different vacua, there should be a localized object, 2 plus 1 dimensional localized object.
Classical solution? I mean, the potential for the axion is a non-perturbative effect.
Yes.
So what do you mean by classical solution?
Okay. So after integrate out the ultraviolet degrees of freedom, so we have the effective theory of the axion with some potential.
The classical solution of the effective.
Yes, thank you. Okay, so and it can be a topological soliton, which can have a topological charge determined by the number of the connecting vacua. For example, this axionic domain wall can has a topological charge 1 because this axionic domain wall connects this minima and this minima. So the number of the connecting minima is 1. So if there is an axionic domain wall connecting this minima and this minima, the domain wall, the topological number is 1 and 2. And the axionic domain wall can be characterized by so-called domain wall number, K phi, which is the number of the minima for one period of the axion. For example, this potential shows that the domain wall number is equal to 4. 1, 2, 3, 4, and this point and this point are identified. And the axionic domain wall is a configuration of the axion, and the gradient of the axion is localized on the domain wall. And the strength of the gradient is given by this. So there is another extended object. So this is a magnetic monopole. So this is a 0 plus 1 dimensional extended object. So this means that the magnetic monopole cannot be annihilated suddenly. So it should be temporarily extended. And so the magnetic monopole can be characterized by the surface integral of the magnetic flux, and this is a charge of the magnetic monopole. And this magnetic charge must be an integer by the Dirac quantization condition. And I'd like to show that these two objects can have non-trivial correlation due to the topological coupling. So for example, I'd like to consider the link of the axionic domain wall and the magnetic monopole. Here, link means that there are no intersection, but they cannot shrink continuously. So I would like to consider the axionic domain wall enclosing a magnetic monopole. In this configuration, we have the induced electric charge on the axionic domain wall. So this is because the modification of the electric Gauss law by the topological coupling. In the presence of the topological coupling, we can write down the Maxwell equation, and we have the induced electric charge from the topological coupling. And since gradient phi is non-zero due to the axionic domain wall, and B is non-zero due to the magnetic monopole, so we have the fractional, we have the induced electric charge.
You're in 4D, of course, and monopole is a warm line.
Yes.
And then you have the domain wall, which is the 3D world wall.
Yes.
What do we actually do?
So okay, sorry. So this is some cross section of the figure. So for example, so here there is a magnetic monopole, and for example, so there is a spherical domain model. Thank you. Sorry. Spherical domain model. So then, so there are magnetic fluxes which intersects.
I'm saying that the magnetic monopole has different electric charge in different vacuums. Because there's multiple vacuums related by the axial shifting.
Sorry. Your question is whether the magnetic monopole can have electric charge or
So what symmetry of there's an axial shift symmetry, which is in fact it's Zn.
yes.
Depends on how you normalize the axion.
Okay, so the global symmetry of the axion is Z K phi in my previous notation. This one.
K phi, what is K phi? How is it related to it?
K phi is the number of the degenerate minima of the axial
I guess
potential.
it depends on the normalization of the axion. How do you
Okay.
identify the axion? The pi plus 2 pi is the compact.
Yes, in my normalization, the axion is normalized by 2 pi.
Are you talking about Young-Mills theory? What's the theory you started with?
Okay, so you are asking about the UV theory. I do not assume the UV theories, and I am focusing on the IR low energy effective theory.
But
So-
you have to some UV theory. I mean, you have to assume it's an
Okay.
SUN. It's
Okay.
SUN.
Okay,
SUN.
for
So,
example, yes.
so then you have to couple the axion properly. I'm guessing you're coupling it like a theta, right?
So axion is coupling to gluons, and
Yeah, but does it have an N in front and so on? How exactly you couple it matters because
okay.
to make this identification. I'm wondering whether do you have a non-anomalous axion shift symmetry or not? You do. It's not related to N. Because the axion shift symmetry is broken by the presence of instant, right?
yes.
The very fact. So a priori you think it's U1, but it's not U1.
Mhm.
It's broken. Is it broken completely, or is there a subgroup which is still a good symmetry?
Okay, so axion, so UV symmetry is broken to ZK, so there is
Okay.
remaining discrete symmetry, and the remaining discrete symmetry is this discrete shift symmetry of the
Okay,
potential.
I still don't know what K is, but then you have multiple vacua, and you're saying your monopole has different electric charges in these different vacua. Is that correct? That's what your picture says. Because there's one vacuum in the middle and the other vacuum outside. That's what your soliton is. Your soliton is a domain connects inequivalent vacuum.
Mhm.
And therefore, in different vacua, your magnetic monopole has different electric charge.
Okay, so you mean that so as in the Tanizaki tank, so there is so for example, so this is theta direction, and so there are some potential, and at theta equals 0, so if there is a 0,
Yeah, I understand. I'm just asking whether that's what you're saying. You're saying that in different vacua, I have different monopoles have different electric charge, so they become diodes. As you cross the domain wall,
It's not like that. That's shorter than 2 pi. That's the 2 pi shift will send green to the other group. Right? Then by within back.
no, but I think this domain wall is not the 2 pi shift. Is the domain wall the 2 pi shift?
That's not the 2 pi shift. It's 2 pi over k shift.
Right. But that gives you electric charge. Right? Cross the domain.
so okay, so
Kinematically, yes.
Huh?
At least kinematically, yes.
Right.
But whether dynamically they can be realized in seven. Okay.
I think.
Or that, I don't know.
So I see. Sorry, so I see. Okay. Yes.
K5 and are completely independent parameter or
K5 and N is completely different. Yes.
so the 2 pi over K5 shift can be anomalous in that sense or
Uh,
K5 is a divisor of N.
Yes, I'd like to discuss this later.
Yes.
Okay.
Yeah.
Yes, okay.
Where's K pi in that dimension?
Ah, So I did not write the explicit language. So for example, 合ってるかこっちか。そう。So this is yes.
Is it? Because that potential is going to be generated by that coupling. That coupling has n. Okay.
Ah.
So I don't know where it.
No. So this is a photon field, not a gluon field. Yes, sorry. So naively, this photon field does not generate a potential, but I would like to explain.
But the potential then by hand or?
Yes. So I put the potential by hand. Yes, and so additional coupling between the photon. Thank you for your question. Okay, so this monopole may be dione because of the different action value. So anyway, so there is an induced electric charge on the axionic domain wall. And this system may be regarded as a dione, and it can be understood as a Witten effect for the axion. So however, the existence of this configuration is non-trivial. So let me explain this. So this is due to this is because the axion potential is generated by the magnetic field. And the axionic domain wall can become unstable due to the magnetic field. So rough explanation is as follows. So the previous electric Gauss law can be solved like this. And substituting this solution into the equation motion of the axion, which can be explicitly written by this. And we have the axion mass generated by the magnetic field. So this can be shown by substituting this solution to this axion photon coupling. So we have the axion field and B square with the magnetic field. So in terms of the Lagrangian, this mass term can be understood as a potential term with n phi. So this potential term gives us n minimum. So this is a very rough explanation. So the number of the minimum of the axion potential is deformed by the axion photon coupling. And the remaining minima is reduced to the greatest common divisor of the axion domain wall number and the axion photon coupling. So the some axionic domain wall becomes unstable. For example, the domain wall connecting this minima and this minima becomes unstable. So this mechanism has been applied to the cosmology. So in cosmology, so the presence of the axionic domain wall is a problem, but so we can solve the axionic domain wall problem by using this mechanism. So they applied this mechanism to to the axionic domain wall problem with monopole dark matter.
Asking what is the goal? Because
Thank you.
even if it's a billion. Although I don't understand this mechanism that you're explaining here. Because in a billion theory, I don't think you generate potential. Do you? You say you do.
Okay, so
But my basic point is that your remaining shift symmetry is exactly dictated by GCD of K.
Yes.
Then, because the original symmetry was not U1, it
Yeah.
was the net.
Okay. So original theory with axion photon coupling is
The axionic coupling is not invariant under the U1 shift symmetry.
yes. So
And then this potential reduces it further.
Okay.
And the only thing that remains is that is in K5.
Yes. So as I said, the invertible global symmetry is the so this is an invertible global symmetry.
I'm saying you didn't put that whole time K5, 5.
Ah,
You just have that.
So yes, so this remaining symmetry should respect this cosine potential, and this remaining symmetry also should respect the axion photocoupling. So the remaining symmetry is this one. So this the GCD K5 comma N is identified as an invertible global symmetry. And I would like to later show that there is a non-invertible symmetry for the axion shift symmetry, and the non-invertible symmetry can be parameterized by the DK5. So let me explain later.
This is in the same way that electromagnetism has a non-invertible U1.
Electromagnetism.
Yeah, this is work by Shupeng Shah.
Yes.
Without that potential, there's a non-invertible, well, U1.
Yes. Exactly.
Something close.
Exactly.
And now you put the potential, and there's still something remaining.
Yes. So this potential exactly remained. Thank you.
By the way, we still don't know whether anything but GCD domain walls are unstable, because as you said, you have to analyze the non-invertible shift symmetries as well, and then there will be associated domain walls, and those walls can still remain stable unless you have a further breaking term for that non-invertible shift symmetries. That was what I'm saying. There's still the entire domain wall spectrum can be ZK rather than GCD.
Yes, domain wall. Yes, so the domain.
You haven't used that much the domain wall yet, right? You haven't added extra.
You're saying this picture may be missing.
Okay, so I didn't add the extra potential term, but this potential term, potential with magnetic field is dynamically generated.
Yeah, so this potential term that you're mentioning that comes from the magnetic field,
yes,
which can also be rephrased in terms of a potential generated from the monopole loop.
Ah,
It can also be rephrased in terms of UV small instantons. This is out UV completion. So they can be generated, but it's not that they will be there yet.
yes.
So I think it cannot be generated if there's this non-invertible field. Right?
Well, there's a
Okay.
non-invertible symmetry, but depending on UV completion, there can be potential which actually explicitly breaks the
Yes.
non-invertible symmetry.
Sure, but I'm saying if that's a UV symmetry, if it's a good UV symmetry, the non-invertible symmetry, then this potential cannot.
Yeah, if it is good, still be close.
Thank you.
Yes.
So this non-inverted symmetry is explicitly broke the dynamical monopole loop. Yes, so thank you. Okay, so this is extended object in the massive action phase. So how about the massive photon phase? So to consider this, so let me explain what are extended object in the massive photon phase. So one of the extended object in the massive photon phase is a magnetic string, which is also called Abrikos-Nielsen vortex or magnetic vortex and so on. So this is a 1 plus 1 dimensional object, and which can be a soliton, which is a classical solution to the equation of motion of the photon. And it is a topological soliton. So the magnetic flux is quantized by the topological charge. So technically, so this topological charge is a winding number, but what is important is that the magnetic flux intersecting this some surface is quantized by this fraction. And this K in the denominator is an integer. So this corresponds to the U1 charge of the Higgs field. And for example, K equals to 2 for the superconductor. So the magnetic string generates the fractional decay Aharonov phase. So in the presence of the magnetic string, we can calculate the this Aharonov phase. And by using the Stokes theorem, we have this fractional Aharonov phase. So this is a magnetic string. And there is another 1 plus 1 dimensional extended object in this phase. So this is an axionic string. So this is also a 1 plus 1 dimensional extended object. So axion string is a configuration of the axion where the axion has a winding number along this line. And this winding number is quantized by the periodicity of the axion. So this is because our axion is assumed to be an energy mode of the global U1 symmetry. Again, so these two objects have non-trivial correlation due to the axion-photon coupling. For example, we consider the linked configuration of the magnetic string, and the axionic string. So this configuration seems to be stable because both strings have topological charges. However, this configuration is non-trivial because there is a fractionally induced electric charge on the magnetic string. So this can be seen by the electric Gauss law. So we have the electric Gauss law in the presence of axion photon coupling, and we can calculate the value of the induced electric charge. So from the axion string, we have this value, and from the magnetic string, we have this value. So this combination is in general fractional. So there is a fractionally induced electric charge. Fractionally quantized electric charge. But this fractional charge violates the Dirac quantization condition. So the existence of such a configuration is non-trivial.
Is it really a string, or is it the boundary of some surface here? Because how do you shift axion as you go around? By 2 pi over k?
No, 2 pi. 2 pi integer. 2 pi integer.
So that's what.
Okay, thank you. So my question is that, so is the above configuration possible or not? So my question in this talk is that what are possible configuration of the solitons in axion electrodynamics? So the linked configuration such as the magnetic monopole and axionic domain mode, or the axionic and magnetic string will be non-trivial. So is it a problem of the dynamics involving the solitons, or there is a universal criterion independent of the detail of the dynamics? So how to discuss it? So we would like to have an exact solution for the linked configuration. However, I think it will be difficult due to the axion-photon nonlinear coupling. So are there any good approaches?
Understand the setup, because are you talking about the photon phase?
Massive photon phase, for example.
So what is a magnetic string? It's gonna be, I mean, it's not a stable.
It's a BF string.
Sorry?
He's thinking of Higgsing the Ionian by
So you're Higgsing, so it's not a photon.
It's an BF string.
Okay. So you're not in the photon phase. You gap the theory completely.
Yes, photon is completely gapped, but axion is massless. Sorry.
Axion is massless.
Yes, but photon is gapped. So yes. So if the axion is also massive, so there is a domain mode inside the axionic string. But in this one, I assume that axion is massless in the Higgs phase. So the axionic string does not have an axionic domain mode. Thank you. I think the completely gapped phase will be interesting.
But either of these two configurations, if I view them as a four-dimensional configuration, meaning instead of, so now I have monopole work line and then domain wall, or I have a two-dimensional worksheet of either magnetic string or axial string, right? And in four dimension, we know that there is no linking number we can define between to an object whose sum of the dimension is exactly E. So this, is there a topological meaning to such a configuration to begin with?
So what is linking in this configuration?
There is no topological invariant associated with that configuration itself, right? Or are there? I don't know. Maybe people don't know.
Mathematically, I think this configuration, this linking is called surface link, or surface. Yes, so it is a link of two surfaces in four dimensions. So and this surface link can be reduced to the ordinary link in the three dimensions. So when we consider the time slice of this configuration, we have the link of the one-dimensional object in three dimensions.
Right.
Yes. So then we just extend this configuration to the time direction. So okay. So this configuration has a topological meaning, I think. Okay. So one of the candidates to approach these problems is the non-invertible and global symmetries. So I think this is the theme of this workshop. Symmetries. Symmetries is the theme of this workshop. So what is non-invertible symmetries? So this is a symmetry whose symmetry generator is conserved as in ordinary symmetries. That is, it commutes with the Hamiltonian. So it is invariant under the time evolution. However, it cannot have an inverse. In particular, it is not a unitary operator. So for example, so the fusion of this operator and this operator, so d and d dagger, is not equal to 1. So what is one-form symmetry? So as Tanitaki-san explained, so this is a symmetry under the action of the one-dimensional extended object. So ordinary symmetry is called zero-form symmetry because it acts on the local operators. For example, a Harlow-Bohm effect on the Wilson loop in vacuum can be regarded as a one-form symmetry transformation. So the conserved charge is the magnetic flux, and the charged object is a Wilson loop. And by the action of the magnetic flux, we have the U1 phase. So here, alpha is a parameter. So what is the conservation law for the magnetic flux? So this is just a Maxwell equation. So in the Maxwell theory, so the number of the magnetic flux is invariant. So the number of the magnetic flux is conserved. So this is the one-form symmetry. So let me explain this in detail later. So the purpose of this talk is that so in the phases where the axion or the photon is massive, we identify solitons with non-invertible symmetry generators. And using non-invertible symmetry generators, we classify possible configuration of solitons with other extended objects. We then derive selection rule for the prohibited configuration by using one-form symmetries. And I will explain the selection rule for the massive in the massive photon phase. That is the selection rule for this configuration in detail. So this is because the linked configuration of the axionic and magnetic strings. The selection rules for this linked configuration is our new result. And the selection rules for the linked configuration of the axionic and magnetic monopole is not new result, but is consistent with previous one. And in the following, I would like to take the low energy limit IR limit to focus on the topological properties of the solitons. In particular, the fluctuation of the axion and photon are neglected, and the magnetic string and axionic domain walls are infinitely thin objects. So topological solitons can have finite width, but we take the low energy limit as a long wave limit or something. Okay. So this is the introduction. Yes.
What operator E is the non-notable operator?
This one?
Yeah. You should say ED never is not one.
Yes. Yes, so this is a non-invertible symmetry. Yes.
Yeah, D is the same as the D down there.
Sorry, so this is in general different. Sorry. So this so I should denote with
What is the non-invertible symmetry operator?
what is a non-invertible symmetry operator?
Explain.
Okay. So non-invertible symmetry is a symmetry whose
Yeah, I know that, but the setup that you described as a figure below, what is playing the role of
I think
okay.
just having one form symmetry there, not non-invertible. Correct me if I'm wrong. I think the lower part is just one form symmetry. There's no none
Sorry.
in the lower part. Non-invertible is described the top.
Yes. So this is these are independent. Sorry. So I should use a different character. Sorry. But later I will explain non-invertible and one-form symmetry. Okay. So this is the introduction. So next, I'd like to review the invertible symmetry in massive photon phase without axion. So this is just a low energy limit of the Abelian-Hicks model. So this section is a review part and based on these papers. So the summary of this section is as follows. So one-form symmetry generator can be regarded as a magnetic string, which generates a Harlow-Bohm effect. So let us consider this action. So this action is the low energy limit of the Abelian-Hicks model. So let me explain the action. The A mu is a photon, which is a U1 gauge field, and field strength F mu nu. Since this is a U1 gauge field, the Dirac condensation condition is assumed, which means that the electric charge and the magnetic charge should be in an integer. And later, I would like to use the Dirac condensation condition. So let me explain this in detail. So Dirac condensation condition states that the electric and magnetic charge should be quantized in U1 gauge theory. So let me explain the quantization of the electric charge. First, I'd like to explain the charge quantization of the Wilson loop. So Wilson loop is a closed world line of a test particle in quantum theory. This one. So in the classical field theory, the test particle is introduced as a line integral in the axion. Here, the coupling constant is absorbed to the gauge field. So when we go to the quantum theory, so we consider the exponential of the action. So the test particle should also be treated as this operator. So this is a Wilson loop. And so we are considering the U1 gauge theory. So since U1 is 2 pi periodic, so the gauge parameter, this one, can have a winding number. So winding number is expressed by this closed line integral. And this is in general non-zero because lambda equals to 0 and lambda is 2 pi are identified. So this closed line integral can be non-zero due to the periodicity. However, this is a gauge symmetry. So the Wilson loop should be invariant under the gauge transformation with winding number. So the gauge transformation of the Wilson loop is explicitly written by this. So we have this deviation. So this deviation can be calculated as this. So this 2 pi comes from the winding number. So the gauge invariance requires that this electric charge QE should be an integer, which is normalized by the electric coupling constant. So this is a quantitation of the Wilson loop, charge of the Wilson loop. So the quantitation for the dynamical particles such as Higgs field is the same. So the charge of the Higgs field should be an integer so that the gauge transformation, this one, is invariant under the periodic shift of the gauge parameter. So in this discussion, the compactness of U1 gauge group is important. So if the gauge group is a positive real number, there are no winding numbers. So any real charge, electric charge is allowed. So next, I'd like to consider the quantitation of the magnetic charge. Here we consider the Antoft loop, which is a closed word line of the test magnetic charge. So the Toft loop can be characterized by the surface integral of the magnetic flux as in ordinary electromagnetism, and Qm is the magnetic charge. So to consider the quantitation, we consider the Wilson loop. And again, we again consider the Wilson loop in the presence of the magnetic monopole. And since this is a closed line integral, so this Wilson loop can be expressed in terms of the surface integral by choosing an auxiliary surface denoted as SC. However, there are many choices of the surfaces. So for example, we can choose SC or we can choose another surface S prime C. However, since the Wilson loop is defined on the line rather than surface, so we require that the Wilson loop is independent of the choice of the surfaces. So that this choice and this choice should be equal to each other. So we have this condition. So the surface integral on the closed surface should be 1. So in the presence of the monopole, this surface integral on the closed surface gives us the magnetic charge. So the magnetic charge should be an integer. So this is the quantitation of the magnetic charge. So this is the Dirac quantitation condition. So let me explain the action. So chi here is a so-called Woodby-Lamb boson of the Higgs field in the low energy limit with U1 charge K. And this chi field is eaten by a photon, and the photon becomes massive. And this also coupling gives us a mass term of the photon. And this coupling is obtained from the kinetic term of the Higgs field. And by taking the low energy limit, we have this condition to have the finite Hamiltonian density in the presence of VA. So the kinetic term and the photon, the kinetic term of the photon and the other Higgs mode can be neglected. So we begin with this action, but to see the one-form symmetry, it will be convenient to dualize this action. So this is the dual action, so-called BF action. So my message is that the mass term of the photon can be dualized to the topological coupling. Here I have introduced the two-form, that is a second-order anti-symmetric tensor U1 gauge field. So this U1 gauge field means that we have imposed the Dirac quantization condition. And this dual transformation can be obtained from the dual transformation of the chi field. So this is basically the Legendre transformation, but let me explain this briefly. So we start with this action and dualize this action. So first we rewrite this action to this action. So by adding two auxiliary fields, C mu and H mu. And the original Lagrangian, this one, can be obtained by eliminating the auxiliary field by the equation motion of H mu. So the equation motion of H mu gives us this condition. So by substituting this relation to this action, so we have this original action. Instead, we eliminate chi field by its equation motion. The equation motion of chi gives us this condition. So H mu can be locally solved by using the two-form gauge field B mu nu like this. So this is similar to the relation in the electromagnetism. So if the divergence of B is 0, so B can be written in terms of the vector potential. So we substitute this solution to this action. And in this action, so the combination between the chi field and B field vanishes because it is locally a total derivative, and its integral is 2 pi z by imposing the Dirac quantization condition for B mu nu, so which is irrelevant in quantum theory. And finally, by eliminating other auxiliary fields such as C mu and taking the low energy limit, we have the coupling between H mu and A mu, and finally by the partial integral, we have this BF action.
Why is F tilde? That's supposed to be curvature of A, right?
Curvature, yes. Yes.
Or is F tilde is dual?
Yes, for the dual. Yes. So okay, so thank you. So it is. Thank you. Maybe I didn't write the definition. Thank you. So this is the Dirac transformation. So by using this dual action, we can find the one-form global symmetry generator by the equation of motion for the photon. Sorry. So this is the one-form symmetry generator. So let me explain how to derive this. So we can consider the equation motion for the photon, and which can be written by this. So since this is a total derivative, we have the conserved current here. So by using this conserved current, we can construct the symmetry generator by appropriate integral and U1 parameter alpha, as in ordinary quantum field theory. However, there is non-trivial constraint on this parameter alpha by the Dirac quantization condition for B mu nu. So as in the case of the electric charge quantization for A, the coefficient of B mu nu should be an integer. So alpha times k over 2 pi should be an integer. So alpha is dk value. So we have this symmetry generator. So let me consider the action symmetry transformation generated by this U1 on the Wilson loop. So in the quantum field theory, the symmetry transformation can be written in terms of the correlation function. So in the case of the one-form symmetry, the symmetry transformation is written by this. So this correlation function means that symmetry generator U1 acts on the Wilson loop and generates the decay phase. And the configuration of S can be seen like this. So if we take the spatially extended surface, so this can be written by this. And if we consider the spatially and temporally extended surface, so the correlation function can be seen like this. So rough derivation of this correlation function is as follows. So we use the electric Gauss law in the presence of the test particle. So the Gauss law can be written by this. So in the presence of the test particle, we have the charge of the test particle. And we substitute this relation to the symmetry generator. And we have this decay phase. So this is a rough derivation based on the electromagnetism. But I will use this symmetry transformation in terms of the correlation function. So let me explain the derivation of the correlation function in detail. So I'd like to calculate this correlation function. So in the path integral formula, this correlation function can be written as this. So this is the BF axion, and this is the symmetry generator, and this is the Wilson loop. And the configuration of S and C are as follows. So this is C, and this is the time slice of C. Sorry. So we want to absorb B mu nu S mu nu by the field redefinition to have the phase transformation. But there are two problems. One is that the symmetry generator does not have a derivative, but the action has a first order derivative. Another problem is that the symmetry generator is a surface integral, but the action is a space-time integral. So I will resolve these problems. First, we can use the Gauss theorem. So we can rewrite this surface integral to the volume integral with derivative. So this will be complicated, but this is just a four-dimensional expression of ordinary Gauss theorem. So this is the divergence of B mu nu. And sorry, what? And this S is a closed surface, and this Vs is a three-dimensional volume whose boundary is S, like this. And B mu tilde is a volume element. Then we use the delta function. So by using the delta function, this volume integral can be written in terms of the space-time integral. So the derivation is simple. So we add the delta function with the space-time integral. And in the presence of the delta function, the argument y can be exchanged to the argument x. So now this term is independent of the volume integral, so we have this expression. And the remaining term is identified as delta nu Vs, which is a delta function which is only non-zero on Vs. So the two problems have been resolved. So the conserved charge can be absorbed into the BF action. So by the partial integral, we have B tilde delta nu. So this is equal to this BF action with shift of the gauge field. Finally, by the field redefinition, this field redefinition, the symmetry generator has been eliminated. Sorry. So this should be B mu nu. So we have absorbed this symmetry generator to the action by this shift. However, this shift gives us the shift of the Wilson loop and generates this classical number. So what is this classical number? In particular, this integral. So this is a linking number between the C and V and S. So S is a surface of the symmetry generator, and C is the world line of the Wilson loop. So this delta function means that this is only non-zero where the C and Vs are intersected each other. This one. So if Vs and C are intersected, S encloses C. So S is linked with C. So this integral gives us the linking number between S and C. Of course, we can rewrite this integral by using Stokes theorem or the green function and we have the four-dimensional expression of the Gauss linking number. So we have the one-form symmetry transformation. So the one-form symmetry generator is absorbed and the Hartmann phase is generated.
X is not yes, it's assumed that it does not wrap around the space bar.
Wrap around space. Oh, so okay. So yes. So I assume.
Yeah. That kind of symmetry generator that are not real cycles.
Yes.
And
yes.
But it how it is, the lithium is 0 or because you cannot stay for
so you assume that so some spatial direction is compactified and like so in this case okay. Okay. But I think so this argument will be important when we consider the topological order or something. So in this case, so we consider the so for example, this configuration. Such a configuration. So by using the time Hamiltonian formalism, operator formalism, so we will consider this such a configuration. So then we calculate the commutation relation between the Wilson loop and the symmetry generator. So the three-dimensional volume can be identified as T2 times. This is a small interval along the time direction.
Yeah, you put the symmetry generator on some T2 cycle, and if you put the anti-symmetry generator, then you can have a three volume that
yes.
Inside.
But they're topological. It's like in the
so you only consider this. In this case, so I think the symmetry generator and the charged object intersected to each other. So I don't have an interpretation at the operator level in quantum field theory. Sorry. So I don't know how to interpret it, how to interpret this configuration. So I think
it's a kind of
so it's boundary condition for the Wilson loop. Gauge field. I see. So we have some So let me discuss it. Thank you. But I think this is very interesting. It is very interesting. Okay. Okay, so this is called one form symmetry because this one this symmetry generator acts on the one-dimensional extended object. And sorry, so the phase factor, this one derived from the previous derivation, is correctly zk valid. So this is due to the Dirac contention condition for the electric charge. And this symmetry is invertible because the symmetry generator is unitary operator. So this is the symmetry transformation. So what is the physical meaning of the one-form symmetry transformation? Or the one-form symmetry generator itself? So so I mean that, so this is unitary because just this is the exponent of the Hermitian operator. So
About this.
So in ordinary symmetry in the quantum mechanics, so for example, so this is so-called, so when so similar interpretation. Yes.
Yeah, that was that case, okay.
Yeah.
You can add multiple surfaces on top of each other. And
Thank
when you add
you.
K, so there's an inverse.
Thank you.
Yeah.
Yes. So
Unitary operator.
So physical interpretation of the unitary operator is that so it preserves the transition probability. So
Unitary representation, because when you take the group element and its inverse, then you get them together and you get identity. It's an invisible, transparent surface. It really is a unitary representation of it. Even in the, do you agree?
yes, so thank you. So later I would like to explain the non-unitary one-form symmetry generator. So then, so what is unitary will be clear. So there are two physical meanings of this one-form symmetry transformation. So one of the physical meaning is the electric Gauss law by taking the spatial extended surface. So this is the same as ordinary electromagnetism. So this symmetry generator just detecting the electric flux emitted from the test particle. So another physical meaning is the Aharonov effect. If the symmetry generator is temporary and spatially extended, and this Wilson loop is spatially extended. So in this case, the invertible symmetry generator U1 generates the phase transformation by inserting the magnetic flux to the Wilson loop. So in the latter phase, the one-form symmetry generator can be identified as a magnetic string, which generates the ZK Aharonov phase. So this is a bit indirect explanation. So let me explain the more direct explanation. So we consider the equation motion of B mu nu in the presence of the one-form symmetry generator. So the insertion of the one-form symmetry generator corresponds to the insertion of this surface integral in the classical action. And in the presence of this term, we can write down the equation of motion for B mu nu. So for simplicity, we take the surface as a temporary and spatially extended GT plane in the in 4 dimensions. So S is extended along Z and T directions. So in this case, the surface integral is reduced to this surface integral. And in the presence of this term, we can write down the equation of motion for B mu nu. And we have this equation. So f tilde dt is equal to the fxy, and this is equal to the 2 pi n over k times delta functions. So this configuration means that the magnetic flux along z direction is localized on the xy plane. So this is a magnetic string. So this is a direct explanation of the physical meaning of the one-form symmetry generator. So the summary of this section is that the one-form symmetry generator can be identified as a magnetic string that generates a hormone effect. So I think this the one area passed. So shall we break?
We're gonna take how long?
5 or 10 minutes or 10 minutes. Okay.
It's something between 5 and 10 minutes. I will yell at you when you come back. Okay, and then we start the second part of the. Okay, so let's take the speaker.
Okay, let me continue my talk. Okay, so I have finished the section 2. So next is the section 3. So now, so we turn on the axion fields. Okay, so no problem. So let me consider the invertible symmetries in the massive photon phase with axion. So this is also a review part based on this paper. So the summary of this section is that the Aharonov phase generated by the one-form symmetry generator are reduced in the presence of the axion photon coupling. And the possible Aharonov phase given by the greatest common divisor of the charge of the Higgs field and the coefficient of the axion photon coupling. So this is the action of the massive photon phase. So we have the massive photon and the massless axion and the topological coupling between them. And in the following, I don't use the kinetic term of the axion. But so I have introduced axion. So this is a pseudoscalar field which is invariant under the periodic shift. So this is because the axion is assumed to be a non-Boson boson for the U1 symmetry. So in this action, we have the axion photon coupling, and this n is quantized. So and physically, this n corresponds to the number of the Dirac fermions in UV theories, which are coupled to axion and photon. So it will be again convenient to dualize the mass term to the BF term. So this is a dualized action. So just replacing the mass term of the photon to the BF term. So by this action, we can consider the one-form symmetry generator by the equation motion of the photon. So this is the symmetry generator of the one-form symmetry. So this is a bit complicated, but let me explain this. So by the equation of motion, we have the conservation law, this one. So in the presence of the axion photon coupling, we have this additional term. But it is still a conservation law. So by the conserved current, we can construct the symmetry generator by the surface integral and adding U1 parameter. However, there are non-trivial constraints on the parameter. And the conclusion is that the symmetry generator is gauge invariant if the parameter satisfies this condition. So this zk is given by the greatest common divisor of k charge of the Higgs field and the axion photon coupling. So let me derive this constraint. First, by the quantization condition, Dirac quantization condition for B mu nu, this parameter should be zk valued. So this is the same as the previous discussion. Furthermore, the shift invariance of the axion requires that this exponential I alpha should be dn valued. So under the shift of the axion, so the surface integral, we have the surface integral of f mu nu. So since the first surface integral of f mu nu is the magnetic flux from the magnetic monopole, so we have a 2 pi integer, and so we arrive at this constraint. So by this constraint, so the symmetry, the parameter of the symmetry is reduced. For example, for k equals 4 and n equals to 2, the capital K is reduced to 2. So the group of the symmetry generator is reduced, and the Aharonov phase generated by this one-form symmetry generator is also reduced. So this is a symmetry transformation by the symmetry generator. So the derivation is the same as the previous discussion, but the generated phase is d capital K valued. So the Aharonov phase is reduced. However, this symmetry is still invertible because the symmetry generator is unitary. So there is a problem. So the possible Aharonov phases are not the small k valued of the and this k is the Higgs of the Higgs charge. So it is not known whether the one-form symmetry generator can be identified as a magnetic string with the small k Aharonov phase. So only the magnetic string with the capital K Aharonov phase can be identified as a one-form symmetry generator. So how about other magnetic strings with the small k Aharonov phase? So is it possible to construct symmetry generators that generate all of the small k Aharonov phase? So the summary of this section is as follows. So the Aharonov phase generated by the one-form symmetries are reduced in the presence of the axion photon coupling. And the possible Aharonov phase is given by the greatest common divisor of the charge of the Higgs field and the axion photon coupling. So let me resolve this question in the next section. So let me explain the non-inverted one-form symmetry in massive axion phase. So our problem is that so the symmetry group of the one-form symmetry generator is reduced. So this problem is due to the axion photon coupling, this one. So naively, the symmetry generator can be written by this. However, there are several constraints for the parameter. For the term from B mu nu, the Dirac quantization condition requires that so this parameter should be z small k valued. So this constraint is physical and okay. So because it correctly gives us the z small k valued Aharonov phase. So this is okay. For the term from the axion photon coupling, the invariance under the periodic shift of the axion further requires this additional constraint. So this is problematic. However, we can avoid this constraint from the axion photon coupling at the expense of the invertibility. So we use the two-dimensional topological field theory. And by using this, so we can resolve this problem. So by using the two-dimensional TQFT, we can modify this term from the axion photon coupling to the partition function of the TQFT. So this is quite complicated, but this is essentially the inverse of the square completion. So let me explain the rough derivation. First, we express this fractional parameter, in general fractional parameter, by the irreducible fraction Q and P. So the 2-pi periodicity of the axion is problematic if P is greater than 1. We then use the modification of the quadratic expression, this one, so that P in the denominator is in the integer. So X corresponds to phi and Y corresponds to F mu nu or the A mu. So in this modification, the P is in the integer. So to do this in the quantum field theory, we add appropriate auxiliary fields, such as 2-pi period pseudoscalar field, chi. So this chi is different from the pseudo-number boson, sorry. And this and further we introduce U1 gauge field living on the symmetry generator. And W mu is the field strength of the U mu, and Dirac condensation condition is required. So in this expression, the 2-pi periodicity is now manifest because P is in the numerator. So this is invariant under the 2-pi shift of the chi field, and this is invariant, and this is invariant. So how about the original expression? So this expression is a naive expression after integrate out the auxiliary field with trivial Dirac condensation condition. So we have a gauge invariant expression or the gauge invariant modification. However, the invertibility or the unitarity is lost due to the sum of the phase factors. So since this is a topological field theory, so this gives us a phase factor. And so, this path integral means that the partial function is the sum of the phase factor. So by this sum, the unitarity or the invertibility is lost. So for example, the cosine function can be 0, which is a sum of the phase factor. So by using this modification, so we can construct the non-invertible symmetry generator. And we can show that this corresponds to the magnetic string with all possible decay Aharonov phase. And the symmetry generator can be explicitly written by this. And now the 2-pi periodicity is manifest by the partition function, but it is non-invertible due to the partition function. And this symmetry generator generates decay transformation on the Wilson loop, as in the previous discussion. So this non-invertible symmetry generator can be identified as a magnetic string with decay transform Aharonov phase. So we have the magnetic string as an okay.
That model, you can think of the non-invertible symmetry generator as a product of something which is completely unitary and very important times a projector, and it's the projector piece which gives rise to the non-invertibleness of the whole operator. Can I think of your construction maybe in a similar way? So next slide.
Okay.
So maybe this exponential thing is unitary, and then it's the GP2 which gives rise to the non-invertibleness.
Yes.
Can I think of it as a projector in some sense?
This GP gives us a projector.
Oh, it's a projector.
Yes, so it projects us the how to say so. So let me explain later. But so this GP projects us the configuration which does not have, which does not satisfy the Dirac condensation condition. But I will explain this. Okay, so this non-inverting symmetry generator can generate the d small k Aharonov phase. So since we have the magnetic string as a non-inverting symmetry generator, let us consider the linked configuration of the axionic string and this non-inverting one-form symmetry generator. So this is the fifth section. So the summary of this section is that using the invertible and non-invertible symmetries, we find the selection rule for the linked configuration of the magnetic and axionic string. In particular, the Dirac condensation condition for the induced charge is important, and this condition can be understood as a selection rule using the global symmetry. So let me consider the linked configuration of the axionic string and non-invertible one-form symmetry generator. And the conclusion is that the correlation function vanishes unless this condition is satisfied. So this correlation function means that this non-invertible symmetry generator acts on the axionic string as a non-invertible transformation. So I think this is the projection for the axion string. So technically, so we can evaluate the TQFT partition function in the presence of the winding number. So in the presence of the winding number, so the partition function, the winding number exists in here in the partition function, and by summing over the dynamical variable u mu, we have the delta function, which constrains the configuration of the d mu chi and del mu phi. So this implies that the winding number divided by p should be an integer. So this is because the winding number of chi should be 2 pi z, and winding number of del mu phi should be 2 pi z. From this delta function, we have this constraint. And by multiplying q, so we have this constraint.
Are you making an operator statement, or you are making a statement? Or are you making an operator statement in the sense that are you doing this drawing as a like operator instructions, or you are actually interpreting action string point as a like defect?
Action string is a defect.
Right, we're now making a statement that if there is the actual defect known as action string, and then what about the D1 part? Is this for you another defect, or it's an operator?
Okay, so D1 is an operator, but in the low energy limit, this defect can be regarded as an operator.
Thinking of actual two constant strings in the sky,
Mm-hmm.
in the universe, then you're making a statement that if there is a one around AB string, the other action string, and then having this particular configuration at prime slice,
Mm-hmm.
you're making a statement that such configuration cannot exist in cosmology. Or you're not making that.
Okay, so this correlation function means that infinitely large time evolution of the configuration of the axion string and magnetic string. So the time evolution of this configuration is constrained. So dynamical creation of this configuration cannot be constrained by this discussion, I think. So yes. So this is because
That's why I was trying to ask whether you're an operator segment versus P.
so in this sense, so this is the interpretation by the defect, not an operator. So no, so operator acting on the Hilbert space. So this is just a defect interpretation. Thank you. Okay, so we have this constraint from explicit calculation of the partition function, but so physical meaning of this constraint will be unclear, at least for me. So let me consider this vanishing of the correlation function in the IR limit. So in the IR limit, the vanishing of the correlation function often means the confinement or the selection rule or something. So how about this case? And I'd like to argue that this is the selection rule. So let me consider this combination. This combination can be interpreted as an induced electric charge on the magnetic string. So this is because the induced charge can be calculated like this. So the gradient phi is equal to the winding number, and the magnetic flux is equal to the phase of the Aharonov effect. So by calculating, we have the same value as this parameter. So if the induced charge is fractional, the correlation function vanishes. So such a configuration may be prohibited by the Dirac quantization condition. So in quantum mechanics, the vanishing of the correlation function can be often classified as a selection rule using symmetries. So is it possible to classify the vanishing of the correlation function for solitons using symmetries? So what we found is that using the inverted one-form symmetry, we have a selection rule for the correlation function. So this is the selection rule for the linked configuration of the magnetic and axionic strings. So we try to detect the induced charge on the magnetic string using the inverted one-form symmetry generator. So our strategy is as follows. So we use the electric Gauss law for the induced charge on the magnetic string. So this is the same as the electromagnetism. So to detect the electric charge or the electric flux from the magnetic string, we put an invertible symmetry generator, this toroidal one, to detect the electric flux from the magnetic string. So this dotted line is the magnetic string, and this toroidal one is the invertible one-form symmetry generator. Then we remove U1 invertible one-form symmetry generator from the non-invertible one-form symmetry generator and shrink the U1 one-form symmetry generator. And in this operation, this non-invertible symmetry generator acts on the invertible one-form symmetry generator and gives us the winding number operator. So this is because A mu in the invertible one-form symmetry generator is shifted by 2 pi n over k, and we have this classical value. And the remaining ones are the axion operator and the derivative. So we have the winding number. And the winding number is given by the axionic string here. So the generated phase from the inverted one-form symmetry generator becomes this classical value. So this is the inverted one-form symmetry transformation for this configuration. However, this generated phase can be ambiguous in general. Since the parameter of this U1 is d capital K valued, the parameter n prime should be periodic under the periodic shift of n to n plus capital K. So the generated phase, this one, should be invariant to this periodic shift. That is, the generated phase should be is invariant if this condition is satisfied. So this can be obtained by just replacing n prime to capital K. So this is 2 pi I, and this term is this term. So the this condition holds only for this parameter is an integer. So if the phase, generated phase is ambiguous, the correlation function itself should vanish to preserve the equality between this and this. So the correlation function vanishes if this constraint is not satisfied. So our conclusion is that using the invertible and non-invertible symmetries, we found a selection rule for the linked configuration of the magnetic and axionic strings. So the Dirac quantization condition for the induced electric charge is important, and this condition can be understood as a selection rule using the global symmetry. So advantage of this argument is that since we are using the symmetries, so our result can be independent of the details of the model. So finally, I'd like to comment on the selection rule for the linked configuration of the axionic domain wall and the monopole in the massive axion phase. So our strategy is the same, so I'll briefly explain. So I'd like to consider this axion. So this is the topological mass term for the axion, and this is the axion photon coupling. And this is the kinetic term of the photon, but I don't use this. So in the low energy limit, the axion potential can be dualized to the topological mass term. So for example, the cosine type potential with domain wall number k phi can be dualized to the topological term with k phi. Here we have introduced the three-form U1 gauge field with the Dirac quantization condition. So the structure is quite similar to the massive photon phase. So just replacing the charge of the Higgs field to the domain wall number and the dual field to B mu nu to the C mu nu rho. So let us construct the symmetry generator corresponding to the axionic domain wall using the equation motion of the axion. So our problem is that can the zero form symmetry generator be identified as axionic domain wall or not? So let me construct the zero form symmetry generator from the equation motion of the axion. The equation motion of the axion can be written as a total derivative. So this can be regarded as a conservation law. And this conservation law can be, by this conservation law, we have the conserved current, and we can construct the symmetry generator. However, so there is a constraint on the symmetry generator, and the symmetry generator should be parameterized by d capital K phi. Here, this capital K phi is the greatest common divisor of domain wall number and axion photon coupling. So this is due to the gauge invariance, including the term from the axion photon coupling. So the zero form symmetry generator is reduced to the d capital K, and this U1 shifts the axion operator by going through the axion local operator and generates the dk phase transformation. So dk phi phase transformation. Therefore, this invertible zero form symmetry generator U0 cannot express all of the domain wall with the dk phi domain wall charge. So this situation is the same as the massive photon phase. So just replacing U1 by U0 and the greatest common divisor of the Higgs field and the axion photon coupling to the domain wall number and the axion photon coupling. So again, so we can construct a zero form symmetry generator with all domain wall charge at the expense of the invertibility. So this can be done by using the modification using U1 Chern-Simons theory. So let me explain this. So this has been done by these papers. So we can modify the term from the axion photon coupling to the partition function of the Chern-Simons theory. So the derivation is the same as the previous one. So we express this fractional coefficient by the irreducible fraction, and we use the inverse of the square completion so that the P prime in the denominator is in the numerator. So to have this square completion, we add the auxiliary field to have auxiliary field U mu. And the gauge invariance is now manifest because P prime is in the numerator. So the original expression is just a naive expression after integrate out the auxiliary field. So by this modification, the unitarity or invertibility is lost due to the sum of the phase factors in the partial function of the Chern-Simons theory. So by using the partial functions, we can construct the non-inverted symmetry generator, and this is manifestly gauge invariant, and this non-inverted symmetry generator gives us a phase G small k phase rotation on the axionic domain, axionic operator. So this D0 symmetry generator can be regarded as an axionic domain wall with all possible dk charge.
So this is related to my previous question too. So when you say by the action D0 as an operator, can be regarded as an axionic domain wall. When you say axionic domain wall, are you saying actual like defect?
Defect, yes. Temporarily extended defect.
So you're claiming that symmetry operator can be identified as a axionic domain wall in the sense that if corresponding symmetry is spontaneous broken, you will get like associated actual cosmological defect, for instance, which is identical mathematical property as the symmetry operator itself. Is that the claim?
Sorry, so
I'm trying to be careful in distinguishing symmetry operator. I'm happy to use Euclidean language. So let me say symmetry defect operator, whichever direction you put.
Yes.
Versus cosmological defect, which has a life, right? In time, it evolved and so on.
Non-topological.
So yes, non-topological defect. So these are a priori a separate thing, which are very much related, because this comes from the spontaneous broken density shift symmetry, whose associated symmetry operator is in D0. Now, when you say, this can be regarded as that, there must be some specification, right? So I just wonder exactly what you mean by regarded as.
Regarded. So I mean that okay, so in the low energy limit, I can regard this symmetry defect as a topological defect. So this is because in the low energy limit, so the width of the solitons can be neglected.
Sure.
And in the low energy limit, the time. So we have the long time limit.
Yeah.
So the topological solitons that have finite life has been decayed.
Yes, I'm happy to take infinite time limit. I am happy to take infinite time limit. So
Yes.
then I even have to treat them as a actual topological defect. Okay, super low energy limit.
Yes.
And yet still your claim, because operator is like, if I take this time slice,
Mhm.
the operator is like that.
Mhm.
Effect is sitting that.
Mhm.
So, but you are claiming that in the infinite time limit or low energy limit, they are mathematically share this identical or same property. That's the claim.
Oh.
That's the same one, or
I didn't consider this issue. Sorry. So
It's really like this, making the, I mean, there's a parameter B in the beginning. Usually most of it's not big.
B, which B?
B, sorry,
Small, wasn't there a small B?
small b, small.
The bad.
Expand, yeah, expand.
Yeah, I'm happy to take that.
Expand is taken to mean.
Yeah.
Ah, yes.
Or,
Yeah.
yes, so, assuming topological.
That I'm happy to take. I'm just asking the subtlety regarding this.
So.
Okay.
So sorry, I didn't.
Yeah,
So let me.
I'm not trying to drag on this, but I'm just question. I'm just curious whether you thought about it. Anyway,
So let me
yes.
discuss later.
Yes.
Thank you. So by using the non-invertible symmetry generator, so we can consider the axionic the linked configuration of the axionic domain wall and the magnetic monopole. So my conclusion is that the correlation function of the linked configuration vanishes unless the magnetic charge of the monopole satisfies this condition. So this can be regarded so this constraint is just obtained by just replacing the winding number in the massive photon case by the magnetic charge Qm. So physically it's the same effect. So there are two ways to show the vanishing of the correlation function. So one is to calculate the Chern-Simons partition function, and the other is to derive the selection rule for the using invertible one-form symmetry generator. So let us use this option. So since in this option, the physical meaning will be clearer. So to derive the selection rule, so the charge of the induced charge on the domain wall will be important. So let us calculate the induced charge. So by the Gauss law, the induced charge is identified as this. And in the presence of the axionic domain wall and the magnetic monopole, the induced charge is fractional in general. So the gradient of the axion is 2 pi n over k phi, and the magnetic flux is 2 pi qm. So we can calculate this combination, and we have this induced charge. So by the same discussion with the invertible one-form symmetry, so we can show that the correlation function with the fractional charge vanishes. So this is the selection rule for the linked configuration of the axionic domain wall and the magnetic monopole. So finally, let me comment on the selection rule for the solitons with finite width. So while we have assumed the infinitely thin solitons, so our results can be applicable to the soliton with finite width. So our assumption is that there are no phase transition between the finite energy scale and the low energy limit. Physically, so this means that the soliton do not vanish by the phase transition. For example, we consider the case of the axionic domain wall. So we can calculate the induced charge on the axionic domain wall with a finite width. So even in the finite width, the induced electric charge can be written by this. Then we take the low energy limit. Since the total energy does not depend on the energy scale by the charge conservation, the total charge is equal to that of the low energy limit, and which can be manifestly calculated by this. So if this violates the Dirac condensation condition, if we would have a fractional charge inconsistent with the low energy limit. So I argue that the configuration with finite width, which violates the Dirac condensation condition, cannot exist. So, okay, so this is a summary of this talk. So, okay, so in the low energy limit of the axion electrodynamics, whether either the axion or the photon is massive, so we have identified the topological solitons as non-invertible symmetry generators in the low energy limit. And by using the non-invertible symmetries, we give selection rules for the linked configuration of the topological solitons and the other objects, such as axionic strings and the magnetic monopoles. And the selection rules are related to the Dirac condensation condition for the induced electric charge on the solitons. And the vanishing of the correlation functions can be classified using invertible one-form symmetry generator. So there are several future works. So let me stop here. So thank you for your attention.